Before we leave chapter 3, we're just going to have a quick little diversion into some stuff about formulas. Not really the best place for it. Well, I guess it's the best place for it. It's not just the totally appropriate place for it. But anyway, talking about formulas, first of all, we can use a chemical formula to get the mass percent of all the atom types that are in that formula. I mean, mass percent is the same as any percent. Mass percent of something X is just the mass of X over the total mass that you've got times 100. So for example, let's determine the mass percent of nitrogen in dinitrogen tetroxide, N2O4. And we got 2 nitrogens and 4 oxygens. So in that N2O4 formula, in a mole of N2O4, in a molecule of N2O4, however you want to do it, you got 2 nitrogens, mass of nitrogen 14, so 2 nitrogens is 28. You then take the entire N2O4, you got 2 14s for the nitrogens, 4 16s for the oxygens, total mass, I hope, of 92. And so the mass percent of the nitrogen is just simply going to be the mass of the nitrogen times 100 over the total mass, 28 over 92 times 100, or 30.4%. Don't you just wish that everything was this easy? Now, of course, we don't have to know the formula of a compound in order to get some mass data. We can do it from experimental data. For example, consider this type situation. We take 1.04 grams of chromium, and I'm nice, I tell you its molar mass is 52 grams per mole, and that reacts with oxygen gas to produce 2 grams of a chromium oxide. So the mass percent of chromium is 1.04 grams of the chromium, total mass of 2 multiplied by 100. And of course, what's the other 48%? Well, the other 48% is the oxygen. Okay, and if we wanted to, we could say that the mass of oxygen in that is 2 minus 1.04 grams. Well, why am I spending so much time talking about the bleeding obvious, as John Cleese said in Fawlty Towers, which if you haven't watched it is, I think, the funniest thing ever on television. Well, let's take that same scenario, right? 1.04 grams of chromium reacts with oxygen gas to produce 2 grams of chromium oxide. We've just seen how we can take these data and get the mass percent, and of course earlier we showed that the mass percent is intimately related to the formula of the compound. Well, let's set up a little chart. We've got chromium and we've got oxygen. The mass of chromium is 1.04 grams. Mass of oxygen, as I just said for that previous example, is going to be 2 minus 1.04, which is 0.96 grams. Soon as you know mass, you can determine moles. Moles of chromium in this example, 0.02 moles, by dividing the 1.04 by 52, and the mass of oxygen is 0.06 moles of oxygen. We just take 0.96, divide that by 16. So in other words, in this chromium oxide, in this pure chromium oxide, we have a 1:3 ratio between chromium and oxygen. In other words, there are 3 times as many oxygen atoms as there are chromium atoms in this species. Now notice that that's just the ratio. We don't know if there's 1 chromium for 3 oxygens in the actual molecular formula, or maybe there's 2 chromiums and 6 oxygens, 3 chromiums and 9 oxygens. But what we can determine experimentally in this way is we can get the ratio between the atoms, and that gives us what is known as the empirical formula. The empirical formula, this is CrO3, it's the ratio of the atom types, and of course it's called empirical because we just derived it experimentally. Let's have a closer look at more of these empirical formulas. Empirical formula defined as being the ratio of the atoms in a molecule as opposed to the molecular formula. So let's set up a little chart, molecular formula and empirical formula, and we'll worry about what I mean by that factor in a minute. Molecular formula, let's say ethane is C2H6. Well, that's the ratio here. We've got 2 carbons to 6 hydrogens, or 1 carbon to 3 hydrogens. And the relationship between the empirical formula and the molecular formula is what I'm calling this factor 2. Okay, the molecular formula has to be a whole number multiple of the empirical formula. In this case here, the molecular formula is twice times the empirical formula. So another one, C6H12O6, glucose. What's the empirical formula of this? Well, 6 to 12 to 6 is 1 to 2 to 1. And to go from the empirical formula to the molecular formula here, we'd multiply by 6. Take another molecule, C2H4O2. This is obviously a very different molecule from glucose, right? This is ethylene diol or ethylene glycol, for example. It's not glucose, but look how it has the same ratio. It's got that 2 to 4 to 2 or 1 to 2 to 1, that same ratio of atoms, the same empirical formula. The only difference in this case is that ethylene glycol, you have to multiply the empirical formula by 2. It's got 2 of those empirical formula units. Glucose, you have to multiply it by 6. Now, we started off talking about the mass percent by mass of such things. And of course we can get the percent by mass, as we said earlier, from the formula percent by mass. For example, in CH3 of carbon is 80, hydrogen is 20. The whole mass is carbon is 12, 3 hydrogens are 3, 12 plus 3 is 15. 12 over 15 is 4/5, which is 80%. And that is the same as the percent by mass of carbon in the molecular formula, right? 2 carbons 24, 6 hydrogens 6, 24 plus 6 is 30, 24 over 30 is again 4 over 5, 80%. We can see that more explicitly with these next two examples. Different molecules that have the same empirical formula, they have the same percent by mass. Let's do another one, N2O4. Empirical formula is NO2. Right, the factor there is 2. The mole fraction is about 30% to 70%. That was the calculation we did at the start. But there's another molecule called nitrogen dioxide. Again, this empirical formula is NO2. Notice here the factor is just 1. Right, there's only one empirical formula in the molecular formula there. Same percent by mass. And then if we go to a formula that we saw in chapter 2, CnH2n, typical cycloalkane. Well, what's the empirical formula of every single cycloalkane? CH2, where N is just the factor, N is the number of carbon atoms, if you remember. And so every single cycloalkane that we will study in this class, certainly 86% carbon, 14% hydrogen. So the point I want you to get out of this is that there is a relationship between the formula of a substance, the mass percent of the atoms in that substance, and what we can determine experimentally in terms of the mole fraction. But that formula that is related to all of these things is not the molecular formula. It's not exactly how many atoms of each type are in a particular molecule. It's what are the ratio of the atoms in that molecule. And given that, we can actually do all kinds of fun things. For example, if we know the percent composition of a substance, we can get the empirical formula. There's obviously a link between them. This is what we've been showing all the way through. So for example, consider a new compound that contains carbon, hydrogen and oxygen. Is found to be 35.3% carbon, 5.9% hydrogen. What's the empirical formula? Let's set up a little chart, shall we? We got carbon, we got hydrogen, and it tells us we have oxygen. They tell us that the mass percent of carbon is 35.3%, the mass percent hydrogen, 5.9%, well, the rest is oxygen. Don't tell us what the oxygen is. How stupid can you get? Okay, well, the answer is you don't need to be told explicitly the oxygen because you've been told it implicitly. The whole thing's 100%, so the oxygen is going to be the 100% minus the 35.5 minus the 5.9, which is, when you add it all up, 58.6%. So how many grams, however, how many moles is what we ultimately want, but how many grams is this? Well, if we consider that we got 100 grams. Take 100 grams. Why would we take 100 grams? Because we know a mass percent. Well, if it's 35.5% carbon by mass, that means that in 100 grams there's 35.5 grams of carbon. There's 5.9 grams of hydrogen, and there's 58.6 grams of oxygen. Once we have mass, of course, doesn't matter whether it's mass in 100 grams, mass in 50 grams, mass in 1,000,000 grams, we can convert that to moles. So our moles in that 100 grams, we got 2.96 moles of carbon, we got 5.9 moles of hydrogen, and we have about 3 0.67 or so moles of oxygen. And so the ratio between these moles, which is going to be the empirical formula, well, this is not quite as easy to see as it might be, but if we divide everything through by 2.96, we find that there's 1 carbon to 2 hydrogens to 1.24 oxygens. That's a ratio, but you of course always want to make a ratio pretty, so we try multiplying this by 2 and we get 2.5, multiply it by 3 we get 3.75, multiply it by 4 and we pretty much get 5. So the actual ratio in nice numbers is multiply the 1 by 4 to get 8, the 2 by 4, 1 by 4 to get 4, excuse me, the 2 by 4 to get 8, and the 1.24 by 4 to get 4.96, which we can pretty much consider to be 5. So the empirical formula that we get from the mass percent, C4H6O5. So we've seen, excuse me, we've seen 2 ways in which we can determine the empirical formula for a substance. We can take some mass data that we get by just doing things in the lab. So many grams of chromium makes so many grams of chromium oxide. We can do it if we're given the percent composition of the different atoms, just like in our last example. Experimentally then, how would one do it? Well, a lot of times you get the analysis of a compound that enables you to ultimately get the empirical formula using something called combustion analysis. Combustion analysis is where you take a sample of your unknown compound, you heat the crap out of it in oxygen, and all the carbon gets turned to carbon dioxide and you trap that. All the hydrogen gets turned to water and you trap that and weigh it. All the nitrogen gets turned to nitrogen oxides, you trap those and you weigh them, and so forth. So let's just do a little example of that. It's nothing new in any of the things we're about to do. There's just a little complicated sequence of processes that we have to do. So 3 grams of a new compound that contains carbon, hydrogen and oxygen was subjected to combustion analysis. We find after putting it through the machine, there's little machines that do all this for you, that you get 6.6 grams of CO2 and 3.6 grams of H2O. Determine the empirical formula. Well, all the carbon in the sample becomes CO2. We have 6.6 grams of CO2, divide that by 44, we get 0.15 moles of CO2. So because there is 1 mole of carbon in every mole of CO2, all the carbon that made this CO2 came from the sample, there was 0.15 moles of carbon present in the 3 grams of the sample. Okay, so there we are. We know how many grams of carbon we got in this sample. We're a third of the way there. Look at the hydrogen. All the hydrogen in the sample becomes water. So we have 3.6 grams of water. That is divided by 18.2 moles of water. But now, unlike the CO2, there are 2 hydrogens in every mole of water. So if we got 0.2 moles of water, there must be 0.4 moles of hydrogen. So in our 3 grams of this new compound that contains carbon, hydrogen, oxygen, we know there's 0.15 moles of carbon, 0.4 moles of hydrogen, with 2/3 of the way to getting that nice little ratio. But what about the oxygen? Again, there is no information given here about the oxygen. And if you think about it, when you combust oxygen, you get oxygen. Right? So there's no way to know, there's no way to measure how much oxygen was produced by this combustion analysis. But of course, that's the only thing we don't know about. We know about the carbon, we know about the hydrogen, so now we can figure out the oxygen. We know that combined are 3 grams, so if we can figure out how much of that 3 grams is carbon and how much of that 3 grams is oxygen, what's left is, we can determine how much of those 3 grams are carbon and how much of those 3 grams are hydrogen, then what's left is the oxygen. So we have 0.15 moles of carbon present. That is equal to 1.8 grams of carbon in the 3 grams. We have 0.4 moles of hydrogen present, so therefore the mass of hydrogen present in the original 3 gram sample is 0.4. So therefore with the oxygen, the mass of the oxygen is the 3 grams with which we started, minus the 1.8 grams we know is carbon, minus the 0.4 grams we know is hydrogen. So we have 0.8 grams of oxygen. 0.8 grams of oxygen corresponds to 0.05 moles of oxygen. So our mole ratio, 0.15 carbons, 0.4 hydrogens, 0.05 oxygens. How do we turn this into a nice pretty number? Well, we just divide through by the smallest number, divide through by 0.05, and we find our mole ratio is actually 3 carbons, 8 hydrogens, 1 oxygen, or in other words, the empirical formula is C3H8O. So hopefully you're now world experts on how we get the empirical formula. We can measure it. We can measure masses that go into making a compound. We can use the mass percent that we can get by various means, or we can just go through combustion analysis. But this just gives us that empirical formula, right? The relative number of atoms, the ratio of the atoms involved. But how can we actually tell which compound of that appropriate empirical formula we actually have? In other words, how can we determine the molecular formula? Well, what we have to remember is, going all the way back to that slide with lots of stuff on it, that the molecular formula and the empirical formula are related by a factor, some whole number, factor, or multiple of the empirical formula. Okay? Now, how does that help us? Well, that helps us because in a second type of experiment, we can actually determine the molar mass of an unknown. We'll look at one way to do this in Chapter 5, another way to do this in the second half of the course, Chapter 13, and so on. There are other ways in which you can determine the molar mass. Well, so what? Well, if the empirical formula is related to the molecular formula by a factor, the mass of the empirical formula is going to be related to the molar mass, the mass of the whole molecular formula, by that same factor. So if we know the empirical formula, we can figure out the mass of the empirical formula. If we know the molar mass, we can get the factor. And if we have the factor and the empirical formula, we can get the molecular formula. So let's do a fast example. A compound with empirical formula CH2O was found to have a molar mass of 148. Determine the molecular formula. Well, the first thing we want is we want to get that mass of the empirical formula. Empirical formula CH2O, C is 12, hydrogens 1 each to 2 plus 16 is 30. So each empirical formula unit weighs 30. Okay? So now putting all this into this relationship here, the mass of the empirical formula, 30, times the factor, is the molar mass, which is 148. Do the math. Factor is 4.93, 148 divided by 30. Seeing as how these are all experimental numbers, let's call that 5, shall we? It's close enough for me. So in other words, the factor is 5. The molecular formula is 5 of the empirical formula. So that's 5 times CH2O. The molecular formula, therefore, is C5H10O5.